Hey guys, welcome back. We got day 34, acids and base reactions. So we're going to dive into acids and bases. All right, there are two definitions. Now we already kind of defined these. All right, what an acid is, right, produces, right, and a base, and that's primarily the Arrhenius definition. All right, so the Arrhenius definition, acid is a substance that produces H plus or H3O plus in water, in aqueous solution. Sorry, in aqueous solution, right? And so we know H plus, H3O plus, that's the same thing. A base is a substance that produces OH minus, hydroxide, in water, in aqueous solution. Now, your common, like an acid would be HCl, base, NaOH, and the reason it's an acid, H out front, reason base, OH, right, metal hydroxide. And so that's the Arrhenius definition. That's the first Chem 1 definition we do. Now, the second definition is the Bronsted-Lowry definitions, right? And technically speaking, this O has a line through it. I don't have that text. I don't know which letter it is. I didn't take the time to do it. But Bronsted and Lowry. And acids and bases are different. An acid is a proton or H plus donor. And the base is a proton or H plus acceptor. All right? And so you're either going to donate an H plus or accept an H plus. And we got lots of examples coming. All right? Now, HCl is still an acid. And hydroxide, NaOH, is still a base, but that's a strong base, right? We're going to talk more about weak bases. So think NH3 is a better example of a Bronsted-Lowry base. All right, so when we talk about this, we got two types of acids, binary acids and ternary oxy acids, if you remember this. So a binary acid's HA, A anything, right? And so this could be HCl to HCN, right? That's that to HC2, H3O2. Well, that is not a binary acid. That would be a ternary oxy acid, right? Because it's written, even though it's written HC2, H3O2, you guys now know bonding. That's an oxy acid. That's actually an organic acid, right? And so, if I draw some lone pairs, right? But these would be like HNO3, right? And they can be monoprotic, which means one H plus, or polyprotic, right? More than one H plus. All right? So, for example, a monoprotic acid, hydrofluoric acid, HF, all right, plus H2O liquid makes H3O plus, right, and F minus. All right. So that would be an example of a monoprotic acid, and that's a great Bronsted-Lowry acid. All right, it works with kind of both definitions, but this would be the acid, obviously, which means water's the base. All right, and now a couple of things here. This is the conjugate acid, all right? And fluoride is the conjugate base. All right. So those are acid-base pairs. Now, something that you see here, that means the reaction can occur in both directions. It's not just a forward reaction where you have A and B going to C and D. Now C and D can go back to A and B, right? And this kind of makes sense. You kind of fundamentally knew this. Some reactions are reversible, right? Like you might be watching this on a device that has a rechargeable battery. That's, not out of the realm of possibility. Or you guys might use, when we breathe, the oxygen goes on into the blood and then comes off the blood and goes to the cells, right? Right? That's an example of reversible reactions that can occur in both directions. So these are acid-base conjugate pairs for the Bronsted-Lowry definition. Okay, so HF's the acid because it donates the proton, and water's the base because it accepts the proton. Now, a polyprotic situation, if you had H2CO3 plus H2O liquid, right, going to, it would be H3O plus HCO3 minus. All right, so again, we have an acid, you have a base, you have the conjugate acid, and the conjugate base. Those are your pairs, right? Those are your acid-base pairs where the proton's going from one to the other. Now, with this, right, this is reaction number 1. Reaction number 2 would be with HCO3 minus carbonate. All right, that's example of a polyprotic acid, in this case diprotic because there's 2, right? There's 2 H's that can come off, right? 1 and 2, right? And the acid base, conjugate acid, conjugate base are the same, right? So, right, that's still an acid, still the base, conjugate acid, conjugate base. Still the same there, all right? So mono and dibasic. What do we mean by monobasic and dibasic? Well, here's 2 examples, sodium hydroxide and barium hydroxide. So sodium hydroxide breaks up in water, right, to Na plus in solution plus OH minus. So it's monobasic. 1 hydroxide comes out. Barium hydroxide breaks up into barium 2 plus 2, right, hydroxides. So that's why it's dibasic, because there's 2 hydroxides that come out. All right. So that's the definitions, right? And what are our bases, right? All right. If we remember, just to recap, right, our acids, you have, I'm going to come over to side 7 strong. Right? If we remember this, hopefully remember this, but HCl, HBr, HI, right? Hydrochloric, hydrobromic, hydroiodic. You got HClO4, HClO3. You have HNO3. So you got perchloric acid, chloric acid, nitric acid, and then sulfuric acid, H2SO4. Those are your 7 strong. All in this course, right? Now, if there's another strong acid, like HPF6, that I would tell you that HPF6 is a strong acid. I'm not going to just expect you to know that. So those are only 7 I expect you to know. Strong bases, right? And hopefully you already have this down. This is repeating. It's just group 1 and 2 hydroxides. right? So lithium, sodium, potassium. Now we're not doing the next two because they're too strong. And we don't do beryllium, but we do magnesium, calcium, strontium, and then barium. So I'll tell you what we'll do. We'll do them in red, because rubidium hydroxide, I don't want to do red. Let's just do a different color, blue. Rubidium hydroxide and cesium hydroxide, these are too strong, right? They are very strong bases. All right, so those are your strong bases. Now, when these acids and bases react, whether it's strong or weak, right? Even weak ones, they're a neutralization reaction, right? That's a reaction between the acid and a base. And the acid, base, salt, water, okay? That's always the case. Now, a lot of times we have to add an indicator. And this changes color when moles of acid equal moles of base. All right, and you get to pick the indicator. That's more of a Chem 2 topic, so we're not going to dive into that right now. But that's what we would do, is that all of a sudden there's a color change when appropriate. All right, so a titration. What's going on with this thing called a titration? It's when a known amount of substance, the titrant, is added to an unknown amount of substance, the analyte, to determine the unknown, usually the concentration. Now, we haven't defined that yet. Our book does it in a little bit. So, right? So the big thing, though, is the equivalence point here, right? Equivalence point, and that's where the titration with the moles, right, equal the moles. All right, so for example, how would we do this set up in a lab? Right, I'd have something called a ring stand. All right, and on the ring stand, I'd have, let's call a flask. And in this flask, there's a little bit of liquid down here, right? Okay, and that flask, that would be my analyte, the unknown. And then we'd have something like this, where you'd have, oh, come on, it didn't snap to it. There we go. All right, you have something that looks somewhat like this. It has a tip on it. It has something to open, all right? And this would be full of something, all right? I'm not going to be able to do the line. It's not letting me do a line. We'll just do it this way. Okay. It's full of something, all right? And this is the titrant. We know this, all right? And we mix them until the moles of titrant that actually enter in equal the moles of analyte. Does that make sense? So we get the same number of moles in the flask. So this equivalence point is when moles of analyte equal moles of titrant in flask. All right, hopefully that makes sense. All right. And then, all right. And so if we look at a basic example, HCl. Let's say HCl is in one of those and NaOH is the other one of those, okay? We have the HCl would be the acid, and NaOH would be the base. Of course, sodium chloride is the salt, and water is the water. Now, remember these ionic equations, the complete and net ionic. What would be the complete ionic equation? Well, HCl is that a strong acid, weak acid is what you look for. You recognize it's an acid, H out in front. You recognize one of your 7 strong acids. So we would get H plus Cl minus. Base, strong base, right? So we get Na plus, right? This is what strong electrolytes do. OH minus. NaCl, the salt. Well, that's ionic and aqueous. It's in water. So you get Na plus Cl minus. And water is a liquid. It's a molecule, so it sticks together. So the net ionic then would be, well, what just reacts? H plus OH minus going to H2O liquid. All right. Okay. And so that's pretty much what we're talking about here with these strong acids, strong bases. All right, so now what do we need to do then about identifying compounds, right? Because that is the biggest factor I found is a problem. What qualifies a salt? All right, what factors qualify a salt? That's a good question. All right, what would you put down if I had wrote? If that was the question, what would you say? All right, because we need to know. Is it, all right, what's first? All right, I need to know what's first. Is it a metal first? Is it a non-metal first? Is it an H first? You know, what are we doing? All right. All right, and so what qualifies salt? It's always going to be a metal plus a non-metal. Right? But there's not, right, H plus in front and not OH minus. All right? Okay? And so I want to know if the following are like, well, before we do that, let's just recap. If you remember the periodic table, something like that, it's got the stairs, right? You got the non-metal, you got the metal, right? And so opposite side of the stairs, far apart, but we don't want hydroxide. Because if we have hydroxide as our anion, that is base. All right, so let's look at these and figure out what they are. I want weak or strong, acid or base. No salts. Salts are just metal, non-metal. All right. So NH3, hopefully we recognize that is the weak base. H3PO4. Hopefully we see the H out in front, so it's acid, and it's not one of the 7 strong, so it's a weak acid. LiOH. Hopefully we see the hydroxide, so it's a strong base. Right? LiOH, strong base. Now, what about this? Hey, I got OH here. No, you don't. You do not have hydroxide. Okay? That's not how that works. So this is formic acid. It's a weak acid. It's an organic acid. And if we look, H to C to O to O to H. All right. Every time you see the COOH, that's what you see. Does that make sense? So hopefully, like, when you see that, that is actually a weak acid. Just like acetic acid, it's the same type of acid. It's the same organic type of acid as this carboxylic acid. That's what they're called. All right. So that's a weak acid. H2SO4 is the next one, and that would be a strong acid. HF would be a weak acid. Barium hydroxide, strong base. And then this last one, what the heck is this thing? All right, what the heck is this thing? Well, the key here, the key is that element right there. Oh, that was fun. Made a square. That element right there. All right, the N. Why is that the case? Now I have an N. I also have an H. But there's no positive. It's neutral. All right, what does that mean? Well, I'm glad you asked. So if I have nitrogen, there's two options for nitrogen. One has a lone pair, and the other one does not have a lone pair. All right, and so even if there's an H here, so what happens with this one, right, if I look, the H, and then there's two of these CH3CH2. So there's a CH3CH2 there, CH3CH2 there, and an H there. And so I have the lone pair still available. That means this is a base. All right. If the lone pair is occupied and I have an H plus, so if there had been a plus here, and that would have been a 3, that would have been a different story. All right. So this was a weak base. Right? And nitrogen is your key. Because that nitrogen, it's the same thing over here. It's the same thing over here with this nitrogen. I didn't want to do all that. Right? This nitrogen here, same thing. Right? That's your key. It's nitrogen, and does that nitrogen have a lone pair? All right, let's do some examples now of Bronsted-Lowry acids and bases. So what's the first thing? I want to know is who's the acid, who's the base? Well, PO43 minus. Does phosphate have a proton to donate? I would say it does not. So I would say this would be the base, which means water is the acid. Now you might have remembered before, I thought water was a base. Water is something called amphoteric, which means it can be both an acid and a base, all right? Because water can accept the proton or donate the proton. Another clue for y'all is that this guy right here, hydroxide is always going to be a base. So right now I know this is the conjugate base. Hydroxide's always the base. Always, always, always. It's, in fact, in this class, it will never not be the base. It's always the base. Which means, if I drew my arrows, right, that is the conjugate base acid pair. Which means that this is the conjugate acid. Because it has a proton to donate. Right, so those are our acid-base conjugate pairs. You look at the next one. All right. Okay, and again, that's always going to be what you think? That's always going to be an acid. That's always an acid. In fact, this is the conjugate acid. I have an acid conjugate, sorry. It should be conjugate acid, right? Which means water then would be the base. And that's the pair. Which means this would be the acid, right? Because it's a proton donor and NH3 is the conjugate base. All right. So ammonium can donate a proton. Ammonia can accept a proton. Water can accept the proton. Hydronium donates the proton. Now, the last one, there is no hydronium or hydroxide. So there's no, like, key. So now I have to figure out what H's can go. So if I look at H's, I see that one and I see that one. So I got two H's here. That's an H, that's an H. Now, on the other side, what's the change? Acetate loses, right? So this H looks like it goes there. And it does, right? The H that was here is now there, right? So if that's the case, that means this is the acid and this is the base. Which means this is the conjugate base. That's a base, right? Because it has no protons to donate, and that's your pair. And we got our conjugate acid. All right? And so knowing the compounds, knowing where the H's are coming and going from, that's a big deal. All right. Balance the following equations and write the corresponding ionic and net ionic equations. All right. So aqueous hydrobromic acid reacting with aqueous ammonia. So this is a time to reflect. Do I know how to name, write the formulas from the names? This is a big deal. All right. So hydro means there's no oxygen. So hydrobromic acid, HBr, back with ammonia, NH3. All right, what's going to happen? Well, I know HBr is the acid, so it's going to donate a proton to ammonia, NH4 plus, and then bromide is left by itself. I want the ionic, so probably the complete ionic and net ionic. And so what happens here? Does HBr break apart? Yes or no? Well, the answer is yes. It's strong acid. So I get H plus Br minus. Does ammonia break apart? Nope, molecule. And then we got ammonium and bromine are already split apart. So we have NH4 plus AQ and Br minus. And so my net equation looks like bromine just goes away. H plus ammonia. Oh. Going to ammonium. So there's our net ionic equation. All right, we can do the same thing. Barium hydroxide. Well, barium is Ba, 2 plus. Now, if you need to go Ba, 2 plus, OH minus, do that. Phosphoric came from 8, so phosphate, PO4, 3 minus. Write all that out. You're not going to get in trouble. In fact, I'd rather see that than not see it, especially when we're learning. So barium hydroxide is BaOH2. Oh, react in solution, so I need to put AQ down. Phosphoric acid, I need 3. H pluses for phosphate. And we're going to switch. So barium phosphate. So barium would be Ba3, PO4, 2, and a state. And I'm okay if you put a solid down, because that's what it probably is. I'm okay if you put AQ down. I'm not okay if you put a G down. If you put a G down, that's wrong. Okay? Because you're not gonna make a gas. And then we have water. Now, is this balanced? No. And so if we look, start with the salt, 3 bariums, 2 phosphates, and so then I'm going to end up with 6 waters. Hopefully we balance enough equations, that's okay, right? Because I always start with the salt. So I have 3 bariums, so I need to put 3 in front of barium. I have 2 phosphates, so I need to put 2 here. And then just look at this oxygen. There are 6 of them, right? So that means I need to put a 6 there. And if you look, 3 times 2 is 6, and 2 times 3 is 6, so that's a total of 12 hydrogens, 12 hydrogens. That's how I like to balance these neutralization reactions. All right, now we need to separate. Now this makes a difference on what state you use. If you use solid for barium phosphate, then it's different than if you don't do it. Okay? And so I'm actually not sure which one your book goes with. All right, and so what we could probably do is look back up at your solubility rules in here. All right, I gotta find your solubility rules. And if we find our solubility rules, which I found, if I see phosphates are generally insoluble, and barium's not listed. So I'm going to put that as a solid. We're actually going to I'm going to erase these, and put it as a solid, and go from there. All right. Your book does say barium hydroxide does break apart, so we'll put 3Ba2 plus AQ plus 6OH minus. Phosphoric acid's weak, so it stays together. Barium phosphate. And water. And if you look, nothing cancels. So that is both the complete and net ionic equation, because we can't cancel anything. All right. So perchloric acid, right? Perchlorate comes from perchlorate, right? So that's ClO4. So we have HClO4 AQ plus MgOH2 solid, right? Mg2 plus OH minus. And it looks like we get magnesium perchlorate, which would be MgClO4 2. And that's probably going to be in solution. Plus, what's left over? I think it's H2O. Are we balanced? I don't think so. I think we need a 2 here. And probably a 2 here. And I think we're good now. All right. 1 magnesium, 2 perchlorates, 4 hydrogens, and 2 oxygens. Yep, that works out. Now, what separates? Here, I have 2 H pluses plus 2 ClO4 minus, 2 perchlorate, plus that stays together, MgOH2 solid. This separates Mg2 plus 2 ClO4 minus, and water stays together, it's a liquid. Well, I can actually cancel perchlorate out. So we get 2 H pluses plus MgOH2 solid, going to magnesium ion in solution, plus 2 waters. Excellent. So that's acids and bases and some of their reactions. Now there's more to it we're coming with soon, because we got more stuff coming. We got, what do we got? We got electron transfer, and then we got concentration. So we got 2 more topics that we're going here in the next few videos. But hopefully that works for you with your acid bases and your acid-base definitions. Make sure you watch this. Make sure you reference your textbook. And let me know if you have any questions. Until next time, guys, we'll see you. Take care. Bye.